Okay, so we can start, okay?
Okay.
The meeting will be recorded, okay? So then if someone else wants to see later on the presentation, I think there will be opportunity, okay? Yeah, so I would like to introduce Dr. Sara Jimenez Alfaro. Recently, she completed a postdoctoral fellowship at Imperial College London with Professor Emilia Martinez Pañeda, where she further developed her research on the effect of surface roughness on fatigue life, an area of strong interest for our group. Today she will give a talk entitled A Computational Framework for Predicting the Effect of Surface Roughness in Fatigue. Sarah, whenever you want.
I can share the screen.
Yeah. Yes. So the floor is yours.
Do you see it?
Yes.
Okay. So yeah, good afternoon to everyone. As Íñigo said, I'm Sara. I'm now a María Sklodowska-Curie and Juan de la Cierva Fellow at the University of Seville. And today I'm going to talk about my work with Professor Emilio Martinez Pañeda, that is an associate professor at the University of Oxford. And as Íñigo said, it is about a computational framework for predicting the effect of surface roughness in fatigue. So first of all, I would like to talk a little bit about my career. Now I'm at the University of Seville. I started 2 months ago. The position I have is considered a tenure track here. Before, I was doing another fellowship in a network that was called Energy for Future, that is now an ongoing network. It is led by Iberdrola, and my base university was Imperial College London, although I was at the University of Oxford for 1 year and a half. I'm a member of the Elasticity and Materials Strength Group at University of Seville, and I'm also an alumni in the international network NewFRAC, where I did a PhD. I was based at Sorbonne University during 3 years, and in this time, I collaborated with Safran and University of Seville. And I would like to use this opportunity to just include a QR code for my new project that is also related to the topic of this working group. It is about the study of the fatigue life of offshore wind turbines, but in this case, the influence of vortices-induced vibrations, and surface roughness plays an important role because it can deviate the vortices and all of this. So it's also an interesting topic for this working group. So now, coming back into the topic, I will start by making an introduction, explaining the objectives and also the numerical framework we have done, the description of the model, the comparison. I will compare my results with experiments. I will describe the surface factor as a function of key parameters, such as the average surface roughness or the correlation length, and then I will finish with some concluding remarks. So I think all of the people included in this group knows that the surface finish is particularly critical for fatigue failure. This is a topic widely studied, and I think one of the starting points was the introduction of the correction factor defined by Marine in 1962. It is the surface factor, and it is defined as the ratio between the endurance limit of the rough surface divided by the endurance limit of the polished surface. This is very clear in materials such as steel, for example, where the endurance limit is really clear. It is the stress level at which we have infinite life. But for materials where we don't have it, normally they put a reference point that is about 1 million cycles. So this surface factor, we can find numerous attempts to estimate it in the literature. We find experiments, but in my opinion, they can be really expensive and sometimes limited. For example, this very famous experimental campaign proposed by Johnson in 1973. They are expensive because to do an SN curve, we need 10 specimens. And if we need to consider the effect of roughness, since it is a stochastic phenomenon, then we need to increase the number of specimens that we use. And they are limited because we have a multi-parameter problem. And although we have the money to do all the tests, we cannot cover all the cases that we have. We also have semi-analytical approaches in the literature. These approaches normally they are related to a notch because the surface topology, the surface roughness topology is very similar to notches. They are very good in static because in the fracture mechanic community we know a lot about notches in static, but when we go to fatigue, then we need to include some empirical coefficients. So in the end, we need experimental data in order to fit these coefficients. So we end up with the same drawbacks as we have in experiments. And then we have numerical approaches, and here the most simple approach was when we approximate the surface roughness profile as a sinusoidal pattern, but the problem is that this is too simple because surface roughness in the end is not sinusoidal, it's not mathematically perfect. Or another approach that we have found is to use a Voronoi tessellation, but in this case we need to consider the grain size of the material that is not something very well known, etc. So in this context, we propose to develop a numerical framework that is able to describe the effect of surface roughness, especially in the high cycle fatigue regime. And this numerical tool is a combination of two different techniques. One is the phase field model for fatigue fracture, and the other one is a stochastic tool to build a roughness resolving mesh. So in the end, what we want to answer is to the question how much fatigue life is reduced for a given surface roughness and material properties. And this is the work that we have recently published in International Journal of Fatigue. So before going into details about the results and also how to build a rough mesh, I would like to explain some details about the phase field model. And for that, imagine we have a bearing tension. At a certain moment, the load is so high that then a crack appears. And this crack can be considered a discontinuity in the material. So the basic idea of phase field is to substitute this discontinuity using a phase field variable that goes from 0 to 1. So we change this discontinuity to a smooth transition. When we have a phase field equal to 0, then the material point is not damaged. And when we have a phase field equal to 1, then the material point is completely damaged. So this is how we change a discontinuity by a smooth transition. We include this variable in the energetic functional of the solid that is defined as the sum of two terms. One is the internal energy and the other one the external work. This energetic function and the solution, the phase field variable and the displacement field, needs to fulfill three conditions. First of all, the reversibility. So the damage cannot come back, basically. The damage variable needs to grow in all the situations. Second one, the stability condition. That means that at each time, the energy needs to be as minimum as possible. And third, the law of conservation of energy. If we join together these three conditions, then we get the solution. The internal energy can also be defined as the sum of different terms. The first one is the elastic internal energy density, that you can see that this is split into two additional terms. This is to consider the fact that only tensile strains promote failure, not negative compression strains. And this is the reason why we have a degradation function only multiplying the positive split term of the energy. And then we have the fracture energy density. So the idea of fracture energy density was introduced by Griffith. It was GC, a material parameter that is the critical energy release rate, multiplied by the crack surface. Here we have a crack surface that is regularized. It is a smooth zone where there a region where there is a smooth transition. So this surface is defined using the phase field variable, as you can see here. We can find different proposals for the definition of these functions. The most famous ones, they are the 81 and the 82. So in the 81 model, we consider an elastic threshold before the damage, and in the 82 model, we consider the damage starts from the beginning. So in the community, we use one or the other one, depending on the approach that gives better results. When we go to fatigue, we need to include in this elastic energy density, another additional parameter, in the energy of the solid, that is the degradation over cycles. It is a fatigue degradation function that reduces the critical energy release rate over the cycles from one cycle to the other. Again, we have different approaches, and we have used the one proposed by Golamar et al. In International Journal of Fatigue in 2023. You can see that this function depends on different parameters, and they are basically the parameters of the basket law, the stress ratio, that is the ratio between the minimum stress and the maximum stress in the cycle, and also this endurance limit. This endurance limit can be in the model just to say to the phase field variable, do not grow if we have a stress level that is lower than the endurance limit, just to consider this infinite life, or we can just omit it and not consider that we have this infinite life, such as other materials. So now we had two different techniques. One was the phase field, and the other one was a tool that is used to define a rough mesh. So this tool is inspired in a proposal made by Loth et al. In 2023. This proposal was for optics, because in optics they are interested in the fact that when the light impinges a surface, then it is deviated if we have a certain surface roughness. So they need to model all of this. And basically, it is the main idea behind this is that we deviate different points in a nominal surface. It means the same surface without the surface roughness, following a mathematical function that is here. You can see that is the product of the root mean square surface roughness, the matrix L, that is the Cholesky decomposition of the autocorrelation matrix, and then the Gaussian white noise. This Gaussian white noise is the one responsible for the stochastic phenomenon. So if we introduce one Gaussian white noise, then we have a certain profile. And if we introduce another one, the surface profile is completely different, considering the same parameters, not the same root mean square surface roughness and the same correlation length. About the correlation length, it is an additional parameter that is here in the definition of the autocorrelation matrix. This parameter is quite interesting because it defines how the different peaks, they are related in the horizontal direction. And we have found that there are different proposals for defining this correlation length. In fact, we highlight three of them. They are related to when the ACF, the autocorrelation function, decays at 10%. When the ACF arrives to a value that is equal to 1 divided by E, where E is the Napier constant, or when ACF is equal to 0.2. So a part of our work is to use the three of them and to see which one gives better results if we compare to experiments. Then here you have how the computational framework looks like. We start by building the nominal surface. It means we don't consider any surface roughness at this moment. Then we consider a certain combination of parameters, average surface roughness and correlation length, or root mean square surface roughness and correlation length. And we obtain the autocorrelation matrix. Then we start an iterative process. So for a certain Gaussian white noise variable, we obtain the distribution of the height of the peaks, and then we build the mesh, assuming that we have a rough specimen. So we just introduce this height deviation in the nominal surface. And then we use the phase field model to determine the number of cycles to failure. We iterate this procedure until we fulfill two different conditions. The first one is that we have at least a sample size of 30. This is because a minimum sample size of 30 gives to us a Gaussian distribution. And the second condition is that the relative margin of error is less than 5%. So if we fulfill these two conditions, then we are done, we are finished, and the number of cycles to failure is the mean of the distribution that we have. So now we compare our results to experimental data. We have used an experimental campaign done by Sain et al. In 2019. It was done on a material that it was IC4130. You can see here in this table the material properties reported. And it was a really interesting experimental campaign because it gives to us all the data we need. So they analyzed, first of all, the polished specimen without any roughness, and then they include two different values of the average surface roughness, and they studied the effect that it has in fatigue. So we start by the polished specimen, and we feed our phase field model, the different parameters that we have in our numerical framework, using just polished specimens. we ensure that our numerical SN curve fits the experimental one. And now we apply the surface roughness. So for that, we have defined the surface factor as a function of different values of the average surface roughness. At this moment, we consider that we don't know the correlation length. We just consider a huge range for a range determined in the literature, as you can see, between 10 and 100 micrometers. This is because we have found that a priori in the literature, we don't find easily this correlation length. So it is just to see how the computational framework can predict data if we don't have this value. And then, as you can see, the two experimental campaigns we have used, the one by Sain et al. That I've mentioned before, and the one by Johnson in 1973, that is one of the most famous ones for this problem, you can see that the experimental data fit always inside the ranges that we predict numerically. At this point, I would like to highlight something, that is that at the beginning I was mentioning the root mean square surface roughness, and now I'm talking about the average surface roughness. This is because here we can work with both parameters, since we are working with a Gaussian distribution, so both are related by this relation. So our numerical tool can be more accurate if we know the correlation length, and this is what we have done here, because in the experimental campaign done in 2019, we have also the surface profile, as you can see here. So we have used this surface profile to build the ACF, the autocorrelation function, and then we have determined using the three criteria the values of the correlation length. So you can see here the results. This is the surface factor obtained numerically, and this is the surface factor obtained experimentally. So as you can see, the one that gives best result is the ACF equal to 0.2, that the error between the experimental results and the numerical results is less than 1%. This is very interesting because this criterion, ACF equal to 0.2, is the criterion used and proposed by the regulation. So it is also the one that gives the best results for us in our computational framework. So each time we are changing a parameter in our tool, what we are doing in the end is that we are changing the rough profile. It means that we are changing the mesh. So here you have some examples. No? For example, this critical case where we have a very big value of the average surface roughness and a very low value of the correlation length. You can see the extreme peaks. Then you can see another extreme case on the other side. That is when we have a low value of the average surface roughness and a big value of the correlation length. And you can see that we can even not notice the peaks. So we need to put a rule for meshing all of these cases, especially because we have a stochastic framework. So in the end, we need to mesh several times in order to get the sample. So this tool is based on the data that we have found in the literature. In the tool proposed by Love et al., they recommended that 5 elements define the correlation length. And in the phase field, it is typically determined that 5 elements define the phase field length scale. So we have just used this compromise relation to determine that in our tool, 5 elements define the minimum, either the correlation length or the phase field length scale. If we change these parameters and we change the mesh, what we see is that the number of elements also change, and it can increase the computational complexity of the problem. So you can see that when the correlation length is really small, then we can have up to 100,000 elements. So it can be a really huge mesh. But what is happening in the end with the phase field model? Here you have it. So the phase field damage starts in one of the peaks, 1, 2, 3, the ones that arrive to the failure, and then the cracks propagate towards the center of the specimen. Then since we are under force control, when a certain region in the specimen is covered by a damage equal to 1, then we consider that the specimen is working, and then we determine the number of cycles to failure. So now we would like to make a parametric analysis where we express the surface factor as a function of key parameters. And for that, we have selected an important range that is the one that we are going to follow in the whole analysis. So we started by the range selected by Johnson in 1973, that, as I've said, I think it is one of the most important experimental campaigns in this topic. And then we have reduced this range in the lowest side, because for average surface roughness lower than 0.2 micrometers, according to the ASTM regulations, the effect in fatigue is negligible. So we have just checked that this is fulfilled for 0.2, and we have not analyzed the other cases. We have also changed two values that are these two ones, to include the fact that in the experimental campaign by Sain et al., it was the average surface roughness 0.5 and 1.5 micrometers. So we have just changed these two ones. And then we have included different values, additional ones, just to have a more accurate analysis and to really get good evolutions for the key parameters. And for the correlation length, we have selected, as I've said before, a range that was found in the literature that was suitable. So now we have built this kind of operational maps where you can see that we show the surface factor as a function of the average surface roughness and also the correlation length. So in this case, you can see that when we have a correlation length that is really big and an average surface roughness that is small, then the effect that the roughness in fatigue has is negligible, almost negligible. But this can be really critical when we go for values of the average surface roughness that they are very big and a correlation length that is small. In that case, we can even arrive to a value that is 0.5. Imagine, this means that for 1 million cycles in the polis specimen, then we have 500,000 cycles of fatigue life for this rough specimen. So it's really, really critical. And since we are working with a stochastic problem, then we also need to analyze the relative margin of error. And this is what we have done here. You can see here the relative margin of error as a function of the average surface roughness and also the correlation length. You can see that in all of this graphic, the value is less than 3.5%. Indeed, this is because we have imposed a condition, I remember to you, that is that this margin of error needs to be less than 5%. So this is why we have this value. And also you can see that this relative margin of error is arrives its biggest value for a big value of the correlation length and also a big value of the average surface roughness. We can also represent this data in a different way, as you can see here, where we just express the surface factor as a function of the correlation length for different values of the average surface roughness, and the opposite case here. And it's very interesting because we can observe that there's not a smooth evolution in this tendency. This is because we are working with a stochastic phenomenon. So as you can see here, we have these bars representing the stochastics. So maybe the smooth evolution is in a point between these bars that we can see here. That's why we have these strange peaks in the evolution. And another conclusion that we also observed in the operational map is that for low values of the average surface roughness, we can obtain a negligible effect even for low or big values of the correlation length of the average surface roughness. So the surface roughness plays almost no role in the surface factor. Here you can see how the relative margin of error and also the number of cycles to failure change when we consider the sample size, so over the simulations. You can see that the margin of error is being reduced when we increase the number of simulations. And also you can see here in this graphic how the average surface roughness plays an important role in the stochastic of the phenomenon. So when we have low values of the average surface roughness, then more or less you can see that the number of cycles is homogeneous. But when we have a big value, then you can see that the peaks are really different. No? So we can get from one simulation to another one really different results. And this is why we need to consider a sample size and this relative margin of error. So the randomness is directly related to the value of the average surface roughness. We have also analyzed the influence of another parameter, that is the fracture strength. And here I need to make an important comment, that is that for the fracture mechanic community, especially for the ones that were working in brittle fracture, the fracture strength is the most important parameters. And since the phase field model was created in this brittle environment, then we use as an input the fracture strength. But when we go for metals, the fracture strength is not very well determined. We don't measure the stress level at which we have fracture. We measure normally the tensile strength, the ultimate strength. That is the maximum stress level that we can get in the tensile test. So there's a bias between our comparison and this one, for example, that comes from this very interesting experimental campaign done in 1973, because they analyze the surface factor as a function of tensile strength, and we analyze it as a function of the fracture strength. But this comes from the fact that in the phase field, we need to include the fracture strength. So here you can see, although it is a different parameter, that we have a common conclusion. That is that for big values of the fracture strength, there is a little influence of the change of the influence of the average surface roughness is less than if we have less values of the fracture strength. This is the same conclusion we can observe here, where you can see that for big values of the tensile strength, there is almost no difference in the value of the surface factor. So we observe similar tendencies, although we are not comparing with the same parameters as I've said before. Maybe now you ask yourselves how we determine this fracture strength, and we use the phase field model. We just fit our SN curve of the polyspecimen. By doing this, we fit what is called the phase field length scale. This is related to the fracture strength, and then we ensure that this fracture strength is just bigger than the tensile strength. So now just to conclude, we have developed a new computational framework that is able to predict the fatigue life of rough components. We have observed a good agreement with experimental data that we have found in the literature. The model is able to create surface versus fatigue map, so we can use it as a design tool. And we have incorporated the stochastic nature of surface roughness by considering the relative margin of error, a sample size, etc. And we don't include it here, but if you have a look on the paper, you can see that we have used our tool to give estimations for additive manufacturing and also pitting corrosion, and we have checked that it fits the experimental data that we have found in the literature. In fact, for the pitting corrosion, I have a former student that finished his master thesis, and we have applied our numerical tool to study different corrosion profiles, and we have determined the fatigue life of this profile. So we have checked that it works in the end. So thank you for your attention, and if you have any question, please feel free.
Yes, thank you very much, Sara. I have a lot of questions and curiosities, but first we open the floor to other people before me. So I don't know if you have any questions. Just open the mic and ask.
Okay, no one, so I will say something. So super interesting, Sara. Thank you for such nice work. Very well explained. Okay, just you're a good speaker, really good speaker.
Thank you.
Okay, it's a very clever way to describe the roughness, right? Because you take both the height and lateral description of the roughness. At first, I thought when we spoke in the Congress, I understood you that you were using RQ, okay?
Yes.
And I was thinking like, okay, but using only height, it's like not enough, right? Because we know that depending on the lateral resolution, you will have like different angles in the valleys, which is like the critical part. So now I can see that the lateral correlation length, it's a kind of fixing this, it's a kind of representing this, which is great. Very nice having this stochastic presentation, so you are able to look at well, distribution and everything. I was just trying to think in the limitations that might have this, which is difficult to find because it's very good.
No, but we have limitations. I can explain to you. Don't worry.
And I was thinking like, okay, this is a very, very good approach for machined and polished surfaces, right? Because you do have like, repetitive patterns and so on. And at the end, you mentioned both additive manufacturing and pitting corrosion.
Yes.
In case of pitting corrosion, I still think it's very good because normally one profile could describe in a proper way the painfulness of the surface, let's say, from the point of view of fatigue. I was trying to think about additive manufacturing because the topographies of additive manufacturing are not such a repetitive patterns anymore. I was also thinking about grid blasted surfaces that probably are not fully described by a profile. I don't know if you do have any approach for, well, including like the 3 dimensions or non-repetitive patterns, like something more like 3D approach.
Okay, yes, I understand your question. Thank you for the comment because actually it's a very interesting proposal. We didn't do it. We didn't do any 3D profile or something. What we did is that we had our operational maps. We took some papers in the literature. We found how to calculate or even if they give the root mean square surface roughness and any value of the correlation length. And we try to see in the operational map if the surface factor that was in according to our numerical tool was fitting the value of the additive manufacturing case or the pitting corrosion, but we didn't enter in modeling all of this. In fact, I think it can be a really interesting topic for the future to apply this.
Yeah, because additive manufacturing is a kind of nightmare for fatigue, right? So having the opportunity to predict what will going on, it's like super interesting. And the very same with sandblasting. In that case, you do have the compression stresses as well. And
yes, the combination
two
of
worlds
residual
starts
stresses.
just having a battle, like who is winning the topography, the compression stress, and so on. But very, very interesting. Thank you very much for the presentation.
I think it's the same for shot pinning, right? That you have these compressive stresses.
Yeah, shot pinning, same. Yeah. I called sandblasting, shot pinning. Yeah.
And for the limitations that you were mentioning, I would like to say that this numerical framework is not suitable for low cycle fatigue in metals because we don't consider plasticity. This is an ongoing work I'm doing. So this is one of the limitations. So it's for retail materials or for the high cycle fatigue regime.
Okay, I see it.
Hello, can you hear me?
Yes, I think yes.
Okay, so I'm Andrea Spagnoli. Sara, thank you.
Hello.
Unfortunately, I was able to attend it for the very few final slides. I was giving lectures, so I missed most of your presentation, but thank you very much. Now, maybe one question that I would like to ask you, if it was in line from the previous question. Did you perform a two-dimensional analysis? So it was an axisymmetric simulation with a plane stress or plane strain conditions.
Yes, it was plane strain conditions. So yeah.
So you were not referring to a circular cylindrical specimen?
No, sorry, I did it. Sorry, I mentioned it wrong. It was plane stress conditions. We didn't have any cylinder or any plane stress.
So
sorry.
All the roughness features were related to the axial direction. We didn't
yes.
yes. Direction.
Yes. This is also a limitation. We need to do also the 3D specimen.
And the other comment was about, you are showing some correlation with the roughness and the material strength in terms of ultimate tensile strength. But I was wondering if you were also considering the hardness of the material, because sometimes, like deepest hardness is relevant for the fatigue strength. So
That's
maybe there
completely
is,
right. That's completely right, but we didn't consider it. Only the tensile strength. But you are right. This could be interesting because they are also related.
yeah,
I have read some papers where they correlate them and they mention it.
yeah, yeah. Okay, anyway, thank you very much.
Thank you for all the comments.
Thank you.
Okay, any more questions? Yes, Hadid, yes.
Hello.
Hello.
Thanks for the talk. It was nice to see something going on WG 4.2. Oh, sorry, 4.4. I am Halit, leader of the WG4. I have noted a couple of things. Let me see. Mainly, when we look at the design point of view as a practical, like a certified engineer, let's say, how much time we need to do this investigation, the computational work flow, to, let's say, in order to be able to like design a real component structure point of view. So this is my first question. And you mentioned that in the beginning, I believe, correct me if it's not not right. The material, like, this is more or less like aiming to studies for material properties not maybe well known, like because I think it was one of the bullet points. And we have seen like mainly the steel examples. So do you have any investigations, ongoing investigations for other type of materials, like including of course the plasticity, like aluminium and etc. And second thing, the last thing is if with your conclusion that the method like phase field, lately we have seen a lot of studies on phase field, but aiming to have some design proposals. So how do you actually see this with the phase field? I can see that from your SN curve, for example, you are just fitting in the mean, but I don't see any scatter. So because fatigue is a scatter, like it's not only the material roughness or some other like physical phenomenon that you are considering here, but how do you like consider the real scatter in the real material in the SN curve, or do you have plan for that?
Okay, thank you for all the questions. Actually, we didn't consider, we just consider an actual test and the surface roughness. It is the only thing we consider, but maybe as a future study. I know that there are real things that are not included in the test, but although they are not included, we have found a good agreement with experimental data, but for sure it would be better if we include all of this. Yeah, I will try to remember all the questions. For steel, yes, in our study, definitely we have used steel, but this is perfectly valid for other materials. I think it's the same, but we change the material properties and it will be the same situation. But yes, and now for the plasticity work, we are using S690 for the numerical validation. And for the last question, how we did it, is a really interesting question because we have an annex explaining this in the paper. We have performed simulations from 3,000 cycles up to 10,000 cycles because since it is a straight line, the SN curve in the high cycle fatigue regime, what we have done is that once we have the straight line, the equation, we have just calculated for 1 million cycles. Just to be sure that our calculations were right for more cycles, we have done some simulations for, I think it was 500,000 cycles, 600,000, but this takes days. So for our simulations, 10,000 cycles is about 2 hours. We know that this is a huge time and we need to reduce it. There are techniques in phase field to do it, such as cycle jump, that we accumulate the energy in the fatigue history, but we didn't try, to be honest.
Can I add one more? But
Yes,
thanks
yes, sure.
thanks for the response. But the parameters, mainly this L correlation and the other, the W phi, like these functions. How do you see, like, when we add the different materials or the inhomogeneity in the same material, let's say, because you are modeling like the material like homogeneous, if I'm not mistaken.
Yes, homogeneous.
Yeah, homogeneous materials. But in reality, we might have different cases, right? Like on the surface, as Andrea asked, like hardness is different maybe on the surface, but compared to like in the bulk material. And also when it comes to shot peening or some other treatment methods, like as you know, they are quite different. Because how do you update this, like in the simulations, or do you have any feelings for that for the future work?
For future work, yes. For our simulations, we don't update these things. For example, I had another work that was in ceramics, but I think it's the same situation where we include the residual stresses and all of this. It's just to include the thermal part of the problem, and it works. So I think it is the same. No, here you include these residual stresses as a compressive stress, just knowing the thermal coefficient, thermal expansion coefficient, and then you will have this together with the fatigue. But this is not considered in our study. So in the future, we would like to do it.
Thank you very much again, Sara. Thank you. Good work.
Thank you.
Yes, so maybe I will be the last one to ask. I have a lot of questions, Sara. First of all, congratulations for the work. I think it is amazing. And something that I really wanted to do with a long time. So yeah, I enjoyed a lot your talk. It seems that the plasticity thing it's a quite hot topic here, and I had also a lot of questions regarding that because the stronger the material, the more sensitive is to roughness effects. So I guess that maybe with the plasticity effects that maybe can be analyzed, those effects. But I will not ask you about plasticity because there were a lot of questions regarding that. My question is like regarding the surface parameters and the fact that so for example in mooring lines, if one of the chains has some defects and suddenly the mooring line will break, and it doesn't matter all of the other chains that were properly, but it was affected regarding some defects. So regarding the surface parameters that you use, the autocorrelation length and array, they are like an average parameters, okay? They are not feature parameters. So my question is, maybe Sara and Alex could answer, can we introduce that like defects or to see some feature parameters that could be analyzed like defects and things like that?
Yes. In fact, I have read papers with that in the bibliography. You can see that they measure the topography of the surface and they directly import this, they build the mesh and then they apply the model. So definitely yes, because the phase field and this technique for building a rough component, they can be decoupled. They can be coupled, but they can be decoupled. They are different models. So the only thing is that if you don't know this surface, then this provides you a solution because it repeats several profiles, so you can have an average measurement.
Okay. That's really nice. So I think so. We can collaborate on that because I'm quite interested on that. So. Okay. So yeah, thank you very much. I think if there is no more question, I don't know if someone has more questions. So, otherwise, we can finish with the first part. Okay. Yes. So we can start with the second part. Okay.